Hello, everybody. We are going to continue rolling right along with another applied optimization problem from section 2.9. And here we go. A company sells Q ribbon winders per year at P dollars per ribbon winder. By the way, I make no pretense of having any idea what a ribbon winder is. Anyway, the demand function for ribbon winders is given by P equals 300 minus 0.02 Q. Now, again, P is the price, and and Q is the quantity, of ribbons, I guess, of ribbon winders. The ribbon winders cost $30 a piece to manufacture, plus there are fixed costs of $9,000 per year. And again, we explained quite a while ago that a fixed cost could be like for the building, for the machine you have to buy, whatever, things which, meaning that 9,000 is, it's going to cost 9,000 whether you make one ribbon winder or a million ribbon winders or no ribbon winders. That 9,000 is that's you're paying that, and it doesn't matter what you do, how much you do. Anyway, we want to find the quantity where the profit is maximized. We want to find the quantity where the profit is maximized. Now, if you notice, we have no equation here that talks about profit. So you know what we're going to do? We're going to make one. So we want to maximize profit, but there's no formula for profit, given here. So profit, as you know, is revenue minus cost. Let me just write this down. Profit equals revenue minus 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 cost. That's a general rule. So let's figure out the revenue, we'll figure out the cost, and then we'll be in business. Okay, so we could find the function for revenue because revenue is PQ. Remember, P is, we saw this in the last problem, small p is the price and Q is the quantity. So the revenue for a given quantity is going to be PQ, but P is going to be P is equal to 300 minus 0.02 Q. How do I know that? Because that's given in the problem. And if I distribute the parentheses, I get R is equal to 300 Q minus 0.02 Q squared. That's R. Let's just hold that for now. The reason I say hold it for now, because eventually we're going to take a derivative of it, but not yet. Let's get the cost first. Now the cost is very simple. It's the 9,000 fixed cost, which we mentioned up here, plus $30 per unit, $30 a piece per, because $30 a piece, $30 per each one. Now we want the profit, and the profit, you guessed it, the the profit is R minus Q. Profit is revenue minus cost. So revenue we already have is 300 Q minus 0.02 Q squared minus the cost, which is 9,000 plus 30 Q. And if you pull this together, combine like terms and so forth, you get negative 0.02 Q squared plus 270 Q minus 9,000. Notice again, this is an upside down parabola. And this is something you learned in algebra, that if the coefficient of the square term in the parabola is negative, means it's an upside down parabola. So we're definitely going to get a max, which is what we want. We want to maximize profit. So there's no question that this is going to maximize profit. But we still got to take the derivative and figure it out and so forth. So let's do that right. Let's do that promptly. The next thing we got to do is to take the derivative of the profit, and that's going to be negative 0.04 Q, negative 0.04Q. I guess I'll write 0.04 just to be consistent. And plus 270. Oops. 270. And I'm going to set this equal to 0. And that's going to give me, well, let's see, what are we going to get here? We're going to get 0.04Q equals 270. Let me turn that into a 0. And then when I divide both sides by 0.04, I'm gonna get the grand total. Let's get a calculator here. So 272.70 divided by 0.04. That is 67.50. That's a nice amount. So we get Q equals 6, and that's the only that's now again. Normally I would say, do the third derivative, do the second derivative test, or whichever. But as you can see, let's do it. Let's not be lazy here. So P prime is just going to equal to, see, this is P right here. So P prime is just going to be equal to negative 0.04, which is always less than 0. It's just a constant. It's less than 0. Oops. So concave down, hence P is a max at Q equals 6750, which is a nice thing. And of course, since this is the only critical point, so it's a global max. This is the global max, and that's it. I don't even have to bother checking the endpoints. There's no other way. There's no other possibility. And there we go. We've done it. QED, POW with but a QED. You may have seen that expression. QED. Oops. I want to go back. Oops. What's going on here? I don't know. Weird. QED is it's actually Latin, and it stands for Quantero Demonstratum, and it just means that we've concluded, we're done. We've demonstrated what we want to demonstrate. It's kind of a fun word. I'm not gonna keep it, but it's kind of a fun word. Alrighty, that was this video, and I'm gonna make another video. I'm gonna do another problem and make another video. Anyway, we'll see you in the next video, and it's been loads of fun. Bye.